Claire, could you run through the general housekeeping, please?
Yep, certainly. I can see the participant list is slowly increasing. So yeah, welcome to the webinar on climate stress testing, and this is hosted by the CIWEM West Midlands branch. So if you experience any technical issues or you need any assistance, then just raise your hand and use the chat feature on Zoom to let us know what the problem is and what we can do to help. If you have problems accessing the Zoom chat, use the Q&A. And then if you could use the Q&A facility to put your questions to the speaker, please. So in terms of some general housekeeping, Ian, could you flick to the next slide? It's not moved yet.
Yeah, sorry, it's just taking a minute to catch up.
Okay. So just to let everyone know that the webinar is going to be recorded, and we put recordings of the events up on the CIWEM website and YouTube when the authors give permission. And if you want to look at any of the past webinars, you can go on YouTube and look for these. If you experience any technical issues, just let us know. We'll be doing questions at the end of the presentation. So if you think of a question during the presentation, just pop it in the Q&A. Use the chat if you've got Zoom-related technical issues. This webinar is an hour's worth of CPD, but we don't provide CPD certificates as it's not CPD accredited training, and this only applies to CIWEM members. So if you just flip to the next slide, please, Ian. So CIWEM is a Royal Chartered Professional body, and it's a charity. CIWEM's vision is of a world in which professionalism and excellence build connections to inspire widespread, impactful water environmental solutions. Barbara will share a few interesting links where you can find out more about CIWEM and the work that we do. I think there's a map on the next slide, which shows the reach that CIWEM has across the globe. And as I said, this event is organised by the West Midlands Branch Committee, and we provide a regional community for water and environment professionals in the Greater Birmingham and the West Midlands area. Our purpose is to provide development and networking opportunities to professionals at all stages of their career. And if you'd like to get in touch with the committee, please go through the CIWEM website. Let us know if there's more of a certain type of event you'd like to see, or if you'd like to get involved. And equally, if you'd like to share something you've worked on, we would be pleased to provide you with the opportunity for a platform in the form of a webinar to share it. And we look forward to hearing from you. So I think I'll now hand over to Ian, who's going to talk to us about the climate stress testing guidance. Thank you, Ian.
Fantastic. Thank you very much, Claire. And yes, a very warm welcome from me this afternoon to our session on climate change stress testing and talking a little bit about the guidance that the CIWEM Climate Change Specialist Panel have come up with and published. We're going to run through quite a few things over the next 40 minutes or so, give you a very quick introduction to myself and the Climate Change Specialist Panel as well. And then we'll spend a bit of time talking through the context and the background to why we thought this stress testing guidance was useful. Some of that will go into sort of some fairly basic detail about climate change. Hopefully that will be useful to any of you who are maybe just sort of starting off working in climate change, and a useful recap to any of you who are already very familiar with the topic. We'll then go into talk about the project itself in quite a lot more detail, why we kicked it off and what our approach was to running it. What is stress testing? We'll discuss that a bit further, and compare it also to what scenario analysis, which it's sort of a subset of. We'll look at the stress testing process that is laid out in the guidance and talk specifically about what is different about climate change stress testing as opposed to stress testing of other inputs, and some of the challenges that brings, and a few specific considerations as well about the use of more or less extreme scenarios and what's also specific to infrastructure in terms of its vulnerability to climate change. So we'll try and whiz through as much of that as possible, as I say, in the next 40 minutes or so, leaving a little bit of time for Q&A at the end. So some quick introductions. As I say, my name's Ian Corder. I work for a company called EPI Consulting, where I mainly work on projects in the construction, infrastructure and energy sectors, particularly looking at supply chain impacts and risks and opportunities. I've been a chartered water and environmental manager since 2018 and a member of the climate change specialist panel for nearly that long as well. My background is a number of roles in infrastructure and the environment, previously for about 4 years running the cost and carbon forecasting function on the Environment Agency's Flood and Coastal Defence Programme. The Climate Change Specialist Panel itself is a body that meets around about every quarter, chaired by Adam Hosking at Jacobs, and we aim to be a focal point for professionals working on climate change issues, particularly in the UK, but around the world as well. And we do input to a number of other bodies on climate change topics, governments and international organisations as well. Obviously, climate change is one of the largest topics that CIWEM members work on, and we do try and assist practically on the topic. So that includes producing a range of policy outputs. We respond to invitations and consultations where we can on behalf of CIWEM, and also some proactive work. So, for example, this stress testing guidance, which we identified the need for and produced ourselves. Obviously, if anyone watching this is interested in joining the specialist panel, very welcome to get in touch. The details are on CIWEM's website. There's a whole section about communities and different specialist panels and interest groups that you can join. So I'll get stuck into the context of climate change and particularly why we felt that stress testing was a useful approach that ought to be considered. Talk a bit about climate change uncertainty, about despite the fact that we're aware of the acceleration of global warming and the likely impacts that will have on climate change at some level, we also know that there are great uncertainties as well. Those can be uncertainties in terms of future policies that can affect emissions, and also uncertainty about the level of forcing that will result from those greenhouse gases. The physical climate state itself is also uncertain, partly as a result of those precursor uncertainties, but also because of inherent variability and uncertainty about the physical climate system. And therefore, the impacts that come out of climate change are also uncertain, the impacts on people and property and the environment. And this is what we call the cascade of uncertainties, which we'll explore in quite a bit more detail in a minute. Now, stress testing is an approach which offers a way to explore some of the more extreme or unlikely scenarios, and we think it could be very useful for that, and already is being used by many organisations that we felt it was helpful to gain some of that best practice from. And so we've produced this guidance that gives really a high-level overview to senior decision makers. It's not a practitioner-level sort of keystroke guide, but it signposts to a lot of other tools and methodologies and data sources that are out there that can be used. As I said, we are looking at this largely through the lens of infrastructure for a couple of reasons, but which I'll explore in a bit. But stress testing obviously is an approach that can be used in a lot of different sectors. It is particularly relevant to infrastructure, though. Infrastructure assets tend to be, many of them are expensive to build and also long-lived. And so decisions made today have to be lived with for many years into the future, sometimes 50 or 100 years. They're often integrated closely into the landscape. So they might be actually subterranean infrastructure, pipelines and cables and all that sort of thing that's underground, or vulnerable to climate change in other ways and the hazards that come out of that. There's also the need for such extensive planning and funding and coordination between different organisations that makes the infrastructure vulnerabilities to climate change a really important one to look at. And of course, infrastructure is very central to many CIWEM members' interests as well. CIWEM members often work for water companies or flood defence organisations or energy companies, and many of these have interests and responsibilities for infrastructure. As I said, I'm going to take this back to really some fundamentals, which should hopefully be useful for everyone, either as a recap or to sort of underpin your knowledge. We're generally aware that global warming continues to occur, and indeed it's reaching new heights. This is data that you can see on the chart there from the WMO recently for 2024, showing that overall, seeing that 23 and 24 being the warmest years on observed record, and indeed the prior decade being the warmest decade on observed record as well, across a number of observations that can be seen in the different colours there on the chart. And indeed, one thing that's very top of people's minds is the 1.5 degree threshold that we've been trying to avoid breaching. In fact, we did see that over the period January through to September 24, there was over 1.5 degrees of warming above pre-industrial levels. We wouldn't say that that is a long-term breach of that threshold, though. The long-term average is closer to about 1.3%, but it's certainly an indication that climate change is reaching the levels that we've previously been warned can trigger some very adverse effects. What we do also know, though, is that as we look out into the future, even as we see the present day emissions increasing faster than we had hoped, the long-range climate forecasts themselves are still uncertain, and they're uncertain in terms of the policies that will be applied, how that will affect emissions, and indeed what the forcing effects of those emissions are going to be in terms of the temperature changes that we observe. The chart that you can see on the screen now is from CMIP5, Coupled Model Intercomparison Project. So this takes a large number of different models and scenarios together in order to provide most likely forecasts and also the ranges around them. And you can see the kind of ranges that we're talking about here in the lighter coloured bars on the chart. So if we look at models that using RCP 4.5, so that's the lightest blue line in the middle, that's showing an average of 2 degrees warming by the end of the century. And I think a lot of people would say that that's probably quite a good case nowadays. Models using RCP 8.5, so that's for those of you who aren't familiar with RCP, RCPs are representative concentration pathways, and the number itself actually refers to the effect in terms of watts per square meter, so the warming effect that's experienced at the Earth's surface. So 8.5 models using RCP 8.5 at the top there with the red line and the pink band around it, showing an average of 4 degrees of warming by the end of the century. But actually, the spread is one of the things that makes us start to really sit up and take note there. Because if everyone knew that it was going to be exactly 4 degrees of warming by the end of the century and could plan for that eventuality, it's a very different situation from where we actually are, where we've got a spread of between 3.5 degrees of warming and up to 5 degrees of warming under that scenario. And there are other scenarios also there as well. We've got other ones that are on the chart there. Some commentators see that current policies, so sort of roughly RCP 6, would give us a warming of between 2.2 and 3.4 degrees, so alignment with current policies. The general takeaway from this is we've got an incredibly wide range of possible future temperatures, and everyone will have their own views about the likelihood of any of these scenarios playing out. But you can see that we're really looking at anything from the sort of 1.5 degrees that we've already experienced right up to 5 degrees of warming, which is obviously a very, very high degree of average warming across the world. Because there's so much uncertainty in those future emission scenarios and what the temperature will actually be as a result, that fairly obviously means that the physical climate system and what that's going to do about it is also uncertain. the climate system responds to the greater energy that's stored in it in a number of different ways, and some of those are unpredictable. Energy gets stored in different parts of that system. Some of it's stored in the air, a lot of it's stored in the sea, and some of it's stored in the land, and gets transferred between them over years or decades or even longer. And there are a lot of feedback processes that we'll look at in a little bit more detail in a minute, such as the growth or the loss of ice sheets that can have, as I say, feedback effects through, for example, reflection. So there can be all kinds of possible climate system responses. And you can see one of those responses that we're already seeing in the global sea ice cover in the chart there, and the range that you see in the grey between 1978 and 2022. Sea ice cover ranging between 17 million square kilometres and sort of up to 27 million square kilometres over the course of a year. And now we're seeing it reaching right at the bottom of sort of approaching 16 million square kilometres in February 2025. I think you're probably getting the theme now that because of the uncertainties that are building up over each stage of any climate model, the resultant impacts on people and property and the environment are also uncertain. And we call this the cascade of uncertainty. And it leads to us really having a huge range of potential future weather events that could happen and impacts that could result from them. And sometimes we can deal with those uncertainties. Sometimes that is absolutely within our modelling capability. But sometimes the more specific you get and the more detailed your outputs are, the less useful those actually become. So there's an example given here, and you'll see that I've put the references at the bottom of the slides if you want to go and look them up yourselves and have a read. But the example given was in modelling of the Mekong River Basin, one of the largest and most important river basins in the world. Where the range of different annual river discharges was from a decrease of nearly 5.5% to an increase of 4.5%. So such wide ranges that really makes it very difficult to formulate a sort of policy response to those. So that's the cascade of uncertainty, quite a useful piece of terminology and visualization, I think, to understand how some of those uncertainties compound as they go through the climate forecasting process. As I said, different aspects of the climate system are potentially very unpredictable. You might ask why that is. Well, in some cases, actually very minor changes in forcing variables that affect the climate can have quite major changes, major effects in the climate system. That could either be because the climate system meets a tipping point, and there's some very good research now that's showing where some of those tipping points are, which parts of the world and which parts of the climate system are most sensitive to moving into a different or a new stable state once they pass the tipping point. Or indeed because some of those runaway feedback effects take hold. So there's a few examples on the slide there, some really interesting ones. One about the collapse of the Atlantic meridional overturning circulation, the most well-known part of which is the Gulf Stream, and some different probabilities that we see of that collapsing if greenhouse gas emissions continue unabated, 30% probability versus if we reach net zero quickly. So it's quite a sensitive part of the assumptions. Loss of sea and land ice, as I mentioned, that's a part where feedback effects are really, really relevant. The sea and land ice affects the albedo, which is the reflectiveness of the Earth. It's also very important in energy transfers as fresh or salty water moves around, and the salinity itself also affects how the climate system responds as salty water behaves differently from fresh water. Permafrost thawing and methane release. You may have heard a bit about this as well, but in a similar way to the loss of ice affecting the albedo on the Earth, but also releasing methane, which can increase the greenhouse gas effect. And then finally, some uncertainties in the role and stability of cloud formations, which obviously have their own reflectiveness and other climate effects as well, but can potentially be quite unstable. So those are just some quick examples of where some of those sensitivities are in the climate system. And I definitely recommend some of those references at the bottom of the page if you're interested more in tipping points and vulnerable parts of the climate system. So if we see then that that there's a very large spread of potential scenarios and potential heating effects and uncertainties about how those heating effects will affect the physical climate system and therefore the impacts on people, it does suggest that perhaps extreme climate scenarios are more important than previously thought. I put the graphic of the day after tomorrow on the screen, not because it's a sort of serious scenario, but because it is something that's worth remembering, that extreme scenarios and unlikely scenarios are still important and relevant, for a number of reasons. One of those might be that perhaps those scenarios are actually more likely than we'd hoped. Necessarily the case, but as we go along, we find actually global emissions are still tracking something not far off RCP, what was expected under RCP 8.5. That doesn't necessarily mean that we'll get the forcing that was predicted under that scenario, or that emissions will continue to rise. But that does seem to be the way that emissions are still going at the moment. Indeed, one study found that there was over a third probability of exceeding the forcing of RCP 8.5 by the end of the century. I'd emphasize that is probably a slightly fringe view, that on the likelihood of exceeding that forcing. But certainly there's our potential fringe scenarios out there. But more importantly, using those more extreme or the catastrophic scenarios means that we understand the parameters of how badly things could go an awful lot better, and particularly about the possible costs of lack of mitigation or adaptation. And more widely, I think there have been concerns raised that extreme climate scenarios aren't being considered enough, or that middle of the road climate scenarios are the primarily ones being planned for. Some authors have suggested that actually the more serious climate scenarios are not talked about as much in IPCC literature, despite the fact that they are increasingly likely. And also because, as I said, some of the unlikely but possible mechanisms that we talked about, some of those sensitivities and tipping points, if they are experienced sooner than expected, could lead to pretty significantly different climate states than we're expecting at the moment, which aren't widely represented in models. Finally, just on this part of the context, I wanted to mention transition risks and physical risks. Hopefully, you can see that the importance of extreme or unlikely scenarios in risk management in general. One thing that I just wanted to point out, and that's particularly relevant to CIWEM members, I think, is that a reasonable amount of focus in the guidance that I'll signpost is on transition risks rather than physical risks. And if you're not familiar with the difference between them, physical risks are the kind of classic climate change risks that we will generally think about: the risks of extreme weather events, heat waves, droughts, flooding, storms, etc., and their effect on vulnerable people or vulnerable receptors. Transition risks are more about the economic effects of what happens as the world goes through a transition into a low carbon economy. So these are actually factors like climate change policies, emission caps, carbon pricing, those kind of things, which are actually policies aimed at managing or mitigating the physical risks. But these sit as risks to some businesses or to some organizations, because they disrupt the status quo and they may make it more expensive to do business. Now, that's sometimes just set as a trade-off between physical and transition risks, and actually the graphic that's on the screen now, which is an IPCC graphic, pretty much it pretty much goes down that path. It is a slightly simplistic trade-off because it's not purely the case that scenarios that are good for business are sort of bad for the planet or something like that. Sometimes it's helpful, but I think it's worth remembering that the overall economic consensus is that this is skewed, so that the physical risks are larger for the world as a whole than the transition risks, and that's one of the reasons why we think that climate policy is justified, why expenditure is justified on correcting climate change. And you just have to go back to the Stern review to see that that climate change policy action is justified economically, indeed spending a percentage of global GDP to address it. So I just mentioned this because I know CIWEM members are likely to be more concerned with physical risks, particularly if we're working in, like I say, flood defence or water resources planning or something like that. But some businesses will be equally or more concerned with transition risks and will see carbon pricing perhaps as a risk to their business model. And some of the guidance, is more focused on that than on the physical risks. And as we sort of start to speak maybe about the finance sector a bit more, that certainly comes to the fore. So I'm going to jump now into the purpose of the project and the project itself in a bit more detail. The bit of the background to it. Obviously, the background, the context that I've just gone through was very key to why we wanted to look at stress testing. But specifically, the Climate Change Committee warned in 2022 that a lot of organisations were struggling to look at climate-related risks in infrastructure systems, particularly where they were highly connected and there was the risk of cascade failures. So a discussion in the climate change specialist panel meant that we decided that we should develop guidance. We should respond to that warning. And after reviewing some of the different approaches that were out there, looking at how organizations were assessing and managing extreme risks and cascade failures, we decided to investigate stress testing as part of that solution. We needed to define the coverage of doing that. We recognised we did have to some extent cut across sectors and the different climate change hazards because we wanted to make this accessible and relevant to a pretty wide variety of people. But we did recognise that a lot of CIWEM members were likely to focus more on the physical rather than the economic transition risks. And so the guidance is focused there. We also didn't want to duplicate approaches, so we've signposted and related it as much as possible to a lot of guidance, whether it's sector specific or not sector specific. The guidance itself is very much senior non-technical. It's aimed at decision makers or non-practitioners really to understand the benefits and the general approaches to stress testing. So that means the format is more of a briefing note rather than a keystroke level handbook. Of course, if there's appetite for more detailed materials in the future, then hopefully that will be something that can be looked at. And we specifically set out to consider cascades and joint risks or interdependencies between assets and organizations. So we started off by recognizing it would be helpful to have a definition of stress testing because it's one of those kind of general usage phrases really that you might use in day-to-day life. But of course, if we're writing a guidance note on it and making recommendations, then we need to define it a bit more tightly. In engineering, it's generally defined as a technique to test the stability of an entity or system under adverse conditions, which is a pretty good broad definition that we drew on. A lot of the guidance, though, is focused not on engineering, but on the finance sector. And here, stress testing has a bit of a more specific definition. It's generally describing processes that regulated entities go through. So banks are told to do this process by regulators in order to manage the stability of the financial system. So it's not necessarily a voluntary process. It's maybe something that entities actually have to do to consider risks such as borrower default and financial contagion. In physical systems more generally, stress testing has, it's done for a purpose. It makes sure that a system is acceptably resilient, which is a really important part of that definition and one we'll come back to, and to identify possible points of failure under specified scenarios. And of course, we do an awful lot of this anyway, or a lot of it is inherent in the built environment. So buildings have to withstand environmental conditions that are imperfect. They're not the day-to-day, rain, snow, flooding, earthquakes perhaps, and do that with a level of confidence over their lifespan. So we arrived at the following definition for the purposes of the project. We said that stress testing is a process for assessing the ability of a system to maintain a certain level of functionality under unfavorable conditions and to understand the consequences if that functionality was not maintained. So there's three important things there, that it's about a system of interest, and that sort of implies something that we can conceptualize and model. It's about maintaining a certain level of functionality. So we have to understand whether the system is in a functional state or a non-functional state. And it's under unfavorable conditions. So we're interested not just in the state in the business as usual, but about scenarios or conditions that are that are not ideal. This does have a lot of overlap with scenario analysis, and if you're familiar with scenario analysis, then you may think, how is this any different? Scenarios are really important. They can help people consider different futures and evaluate them and make plans in response to them. And a lot of the guidance there about climate change doesn't particularly mention stress testing. So the original TCFD recommendations don't really mention stress testing, but they do go into a lot of detail on scenario analysis and what the benefits are to a business or an organization in evaluating a range of different futures that could come out and what they would do in response to those. However, what we did find was that there was generally not a requirement that those scenarios should be extreme. Although the technical supplement for TCFD does talk about stress testing in some of its examples, as we kind of got into the more detail on the different parts of guidance, we found that there was a lot of useful guidance that was about scenario analysis, but maybe didn't specifically encourage users to consider sufficiently adverse scenarios as part of that. So the visualization on the right just helps sort of frame this. I think that scenario analysis is a larger concept of visualizing and considering the future in different ways, and it often considers business as usual as one of those scenarios, whereas stress testing is kind of a subset of this and really focusing those scenarios on the more extreme ones. The stress testing process that we've come up with is in 6 steps, and I say we've come up with it. We've adapted it from generic stress testing guidance from the IMF and the World Bank, but we do feel that it's applicable generically across financial systems, engineering systems, and indeed other kinds of systems that you could imagine. Integrated organizational and infrastructure systems, for instance. Anything that can be adequately conceived, adequately conceived and modeled. Now, the principles, before I get into the 6 steps, there's a couple of principles that were pretty key from the guidance that we found. Firstly, that tests need to be carried out at an appropriate system level, because that's the only way to consider dependencies and cascades. That means that the system that you choose of interest to model and to carry out a stress testing on may not be exactly the system that your organization is responsible for. You might need, in sort of purely financial or legislative terms, you may need to consider the interactions with other parts of a wider system, such as other organizations that you work with. And this is quite obvious, because actually, you will almost always have dependencies on your suppliers and your supply chain, even though they're outside the boundaries of your organization. And tests should also be transparent about the robustness of their assumptions. So that's something that we come back to quite often, because there's uncertainty in a lot of the scenarios that I was talking about earlier. It's really important that we are transparent about how much confidence or uncertainty we have in the conclusions being drawn from stress testing as well. So the 6 generic steps that we came up with, number 1 is about identifying specific vulnerabilities or areas of concern. Number 2 is about constructing or selecting a scenario. It may be a scenario that you pull off the shelf. It doesn't have to be an entirely new one. Number 3 is about mapping that scenario into an analytical form, and that could be all kinds of different formats that you might do that in. We'll talk in a minute about some examples of that. But a quick example would be that a stress test for a bank is probably going to involve the financial institution's balance sheets at the end of the process. So that would be part of your scenario documentation. You then perform some sort of numerical analysis, and this does again rather come back to the guidance that are coming from the finance sector. You could perform a non-numerical analysis. You could perform a qualitative approach to this. But I think we're generally assuming that people are attempting to quantify these and put numbers into the analysis and out of the analysis as much as possible. Step 5 is considering any second round effects, which is an interesting part of the process that we'll talk about in a second. And step 6, summarizing and interpreting the results for onwards communication, which is obviously really, really key. That the outputs of a stress test don't just sit in a locked bottom drawer somewhere. So to dive into those different steps in a little bit more detail, I said that step 1 is about identifying those. There's always a balance to be struck here because you're almost always undertaking a stress test with some understanding already of where you think the system's vulnerabilities are. And you need to do that in order to model areas of interest in greater or lesser detail, because you can't represent everything, in your system of interest in the same detail, and it wouldn't be appropriate. The trade-off from that, of course, is that if you were wrong about where the vulnerabilities are, then you might make inappropriate choices in which parts of the model you focus on. So there's a reminder here that sometimes iteration is the best point. Once you understand the sensitivities of your system in greater detail, you may want to go back and redo a stress testing process with that in mind. Step 2, about constructing or selecting a scenario. So as I said, we really commend the TCFD technical supplement on scenario analysis as a starting point, but that is absolutely only a starting point. There's all kinds of scenarios available. There's the NGFS scenarios and the shared socioeconomic pathways, which is sort of the default now, I think, really, the SSPs. I'm not going to go into an awful lot of detail on choosing those different scenarios. I'll talk about extreme scenarios in a little bit more detail later on. But suffice it to say that there has been an awful lot of development of good quality scenarios from either purely from a climate change perspective, or indeed scenarios with inputs from the IEA, looking at future energy mix, for instance, which would be more relevant to those of you who are considering transition risks, perhaps. As I say, in stress testing, organizations are generally going to be interested in lower probability, higher impact scenarios. So yeah, this is why I emphasize things like RCP 8.5 and the associated SSP 8.5. Step 3, about mapping the outputs of the scenario into a form that we can use for analysis. So that can be as simple as representing your conceptual model in an Excel workbook, and an awful lot of the models that I've seen are exactly that. They're a representation of how your system of interest responds to changes in its inputs, and some of them, sometimes simple, can be very, very good if it's helpful in terms of what you're trying to find out. Sometimes you might need something much more comprehensive than that. You might need some kind of physical modeling or representation of the climate at the start of the process. So, for example, if you were looking at the vulnerability or the stress testing of a food system, for instance, then you would probably want to take some outputs from future climate change weather projections and see how that affected crop yields over the future. And then you might also have responses in terms of prices of agricultural commodities or something like that. As you can see, it could be something that had a number of different steps, or it could be something that became part of a design process for a new piece of infrastructure, for instance. It's really important through all this, though, to understand and define what constitutes failure. So I mentioned this earlier on, that a key part of the definition of stress testing is understanding when a system does fail, in order to explore the scenarios that could actually cause that. And I think that's not always as easy to do as you might imagine, because it's sometimes easy to say what we would ideally like to a system to perform at, but when do we actually accept that its performance is inadequate? And then there was a good report from the Joint Committee for National Security, and I can't remember what the other S is, JCNSS anyway, referencing some of the resilience standards of infrastructure. And just at the bottom there, I've put in some of them as examples. Some of them are more about uptime, the amount of time that users of a service can enjoy the benefits of it. So the amount of time that, your drinking water is on or your broadband is supplied. some of them are more about the ongoing quality of the supply instead. So it could be about not just the fact that drinking water is provided, but that it meets a particular quality standard, or that road users can not only use a road, but that they can experience a journey time that's adequate to them. So it's really useful, I think, for different organizations to think in more detail about what does constitute success or failure, and what are the thresholds at which are unacceptable failure, in order to consider what they're aiming at for stress testing purposes. What kind of failure is bad enough that we want to consider it for stress testing. And then some reminders then about how you do modeling in general. So determining the accuracy and usefulness of a model, and how you can validate it as well, which is quite a lot more detail. Step 4 is about performing the numerical analysis. So I won't give too many examples here, but if you were doing this in a Monte Carlo analysis, then you would be iterating a whole bunch of probability distributions and trying to predict what the likelihoods were of different future outcomes. Step 5 is considering any second round effects, and this is really interesting. Second round effects are when there's some kind of interaction between how the model runs in the first time, and then decisions from other people. So, for example, if a model predicts price changes, how would they be passed on, and how would other people respond to those? I think in an infrastructure system, this step could be used to consider those interfaces and dependencies with other organizations. So, assuming that in a particular stressful scenario, your system behaved in a particular way, would that affect how other infrastructure operators or other people went about their day-to-day? For example, if one part of a road network fails, that actually quite often implies that there'll be greater usage of other parts of the road network because people shift their journey patterns. And this is where we can start to address those cascade risks. So identifying the potential for a failure in one part of a system to lead to a failure in another system or another part of a larger system. And then finally, step 6, which is about summarizing and interpreting the results. So it's not just good enough for a model output to be concise and useful and provide some kind of insight into the stressful scenarios that would cause failure. But of course, those outputs have to be useful to decision makers and stakeholders as well. So, and often their input is what will then cause the model maker to reevaluate how they've gone about representing the system. So, again, that is where iteration is quite often helpful. Said that we talk specifically about challenges in climate change stress testing. Some of these are probably not very surprising. We know that climate change stress testing has to go out to longer horizons than most other forms of stress testing. With climate change, you're generally thinking about risks out to at least sort of 30 years, while financial stress tests are actually only normally carried out to about 5 years or so. So there's going to be a different kind of focus there when you're just considering, the financial stability of banks, for instance, surprisingly short term. And some of the other considerations are probably unsurprising. We have to deal with a lot of uncertainty in climate change parameters and observations, as well as the uncertainty that I talked about in how different people respond or are able to respond. So a practical question then is, well, how rare or extreme should the scenarios be that we're considering? Well, the easy answer, I'm afraid, is that, but not particularly useful, is that they need to be extreme enough to test the resilience of the system of interest. And that's why understanding about what constitutes failure is really important. It was notable, though, as we started to look at some of the literature and guidance, was that actually some of the scenarios covered by, for example, the Bank of England's 2019 insurance stress test didn't have probabilities accompanying them. So they were essentially bare scenarios without sort of an opportunity for respondents to use the probabilities in their own modeling. So what we would suggest is that if you're undertaking climate stress testing, it's always worth considering the severe but unlikely scenarios, and that's not just as simple as saying, well, always consider RCP 8.5 or SSB 8.5 as well. It's also understanding, well, what happens in the more fringe cases there in your specific situation. So don't dismiss scenarios or possibilities that are flagged as very unlikely or extremely unlikely or exceptionally unlikely, because actually increasingly public infrastructure does have to consider less than exceptionally unlikely events. So drought planning, for instance, now is considering the 1 in 500 year events in terms of water company resilience. We already have public guidance stating that safety critical elements of infrastructure have to be assessed against high impact, low probability scenarios. So we're probably actually talking about scenarios that are at least extremely unlikely or possibly exceptionally unlikely when we're looking at stress testing, particularly, as I say, when building long-lived infrastructure that needs to be got right for a large number of years. If I say infrastructure is particularly vulnerable to climate change, some of those characteristics I've already mentioned, that they're costly and long-lived assets that are often particularly vulnerable to the physical climate change hazards. And there's a couple of examples there that probably very familiar with. The Tewkesbury flood at 2007, and some interactions there between different parts of infrastructure systems, water treatment works and electricity both being affected, and of course transport networks as well. And also Storm Arwen, not 2007, that's a mistake. It's much more recent than that, but which left more than 1 million homes without power. And interestingly, a good example of a cascade risk there, because the disruption to the electricity grid also meant that a large number of people ended up without heat, water, and phone services. In fact, 17,000 people without water as a result of water company assets being unable to function without the power, and phone services that people required to call emergency services not being available because they required electricity as well. So some really good examples there, I think, of the joint and interdependencies and so I'll wrap up quickly because I want to leave a little bit of time. But the overall project findings and challenges, in terms of our findings, we were already very pleased. There was such a large amount of guidance material already available. And that meant that the stress testing guidance that you can now find on the website is definitely only a starting point. We boiled down a lot of what we found into about 15 pages with an awful lot of signposting and references to other useful documents. So it's certainly not a comprehensive treatment of stress testing as a process, but I still think it's a very, very useful starting point. As I said, the TCFD technical supplement on scenario analysis is also a really good starting point. It's only about 40 pages, and it covers both physical and transition risks. But I do highlight that focus there, that a lot of the focus is on transition risks, particularly for sort of financial services companies, and that those transition risks do come with a different mindset and different time scales and different drivers compared to the physical climate change risks. In terms of where we think this could go in the future, I think producing this at the level that we did, purely with volunteers, meant that we had to do it at a fairly high level, and there would be value in generating practitioner level outputs. So actually reviewing some of the specific data sets. So we weren't really able to reference stuff that was very country specific. UK CP projections, for instance. It would be good to understand more about how those are being used in practice, and the different scenarios, the more extreme and unlikely scenarios that can be used there. it would be great to have some more detailed case studies. We were able to get about 4 case studies, I think, from a few organisations. But again, it would be great to see that in more detail, how different organisations are undertaking stress testing or undertaking analysis that is akin to stress testing. Because when we looked at it, we did find several organisations that were using 4-degree warming scenarios, for instance, which is a fairly sort of extreme warming consistent with RCP 8.5, or the middle of RCP 8.5 anyway. You could argue that even more extreme scenarios should be considered. But yeah, the more case studies we have, the easier it would be to really benchmark different organizations and the approach across the country, and be able to say, well, what scenarios are people really considering, and are they sufficiently adverse at the moment? It would also be great to give some more focused guidance on compound risks and infrastructure codependencies, because we were able to sort of talk about those in principle, but it would be great to have some more specific examples of where different infrastructure organizations depend on each other, and what the best practice is on assessing and managing those collaboratively. I think that would be a really helpful thing to look at in the future. So hopefully that's been a useful overview. I'm conscious that we have slightly less than 10 minutes now in order to cover Q&A, but I'm very, very happy to answer any questions that have come up. Or indeed, I've also included some thoughts that attendees might like to think about, either just to reflect on yourselves and take away to your organizations, or if you want to share them on the call today about any climate scenarios that your organization has considered, whether they're extreme or not, that would be much appreciated. But yeah, I'll answer any questions now if they've come up.
Thank you, Ian. That was really interesting presentation. I definitely say, having read the guidance before the presentation, it was really great to get a much better understanding of the context and the reason for producing the guidance, as I definitely think that gives you a much better appreciation. So thank you. There isn't anything in the Q&A as far as I can see. Oh no, there is. One's just popped up. Excellent. So James is asking, the Thames Estuary 2100 uses the RCP 8.5 95th percentile sea level rise as a design assumption for climate change interventions. And it says we use H++ for sensitivity testing. I think it doesn't. I think that's just
Brilliant.
a comment rather than a question, I think, there, unless you've got any comments on that.
That's great. Yeah. Thanks, James. Thanks for sharing that. That's really useful to have. I'd be interested in, actually, when you say RCP 8.5 95th percentile, 8.5 I think was already a 90th percentile scenario. So I wonder if that was, are you sort of taking the 95th percentile beyond that, or exactly how that works? I'd be interested to know. I mean, you're saying approximately a 4-degree rise, which would suggest to me that was RCP 8.5 50th percentile, I think. But yeah, so I'd be happy to pick that up with you offline as well, if you wanted to discuss it at all. And interesting to see as well that you've got a defined way for approach for sensitivity analysis. I think that's a really useful part of scenario analysis in general, actually, that sometimes gets that does sometimes get ignored because people aren't sure how to interpret the results. But the sensitivity of any model to the inputs that it's receiving is such an important thing to know, and particularly with stress testing, because if your sensitivity helps you identify which parts of your model are really driving the outputs of it, and you can see whether that actually is true in real life, it can really help you identify some vulnerabilities in the system of interest. So that's great to hear you're doing that. I'm not actually familiar with H++, so I'm not sure if that's a sort of analytical package that comes as part of the design, and then gives you things like tornado charts, which is how I've previously seen sensitivity analysis done. but I'll look it up after the call. And thanks for sharing that with me.
Okay. So James has just responded to say that it's the UK CPC level rise projection, and so yeah, you can find it online.
Lovely.
I guess.
Thanks, James.
I guess you kind of part answered one of the questions I had, which was around the case studies. And I think it was interesting to see how people had applied this guidance. And I know you said something you'd like to do. If people wanted to contribute to this, is there a way they could do that yet, or is this something that's you're going to have a more formalised way of trying to collect those case studies in future?
Yeah, I mean, I can certainly say I'm always open to. If anyone wants to share those with me at any time, I'm very happy to collate them. We haven't sort of restarted a process for pulling more guidance together or putting those case studies into anywhere specifically. But personally, I'm very happy for people to reach out and sort of provide those contacts or that information at any point. And I'll share my email address and stuff on the screen. Well, I'll share it now, actually, just so that people can have it. Because I kind of hope that we will get to that stage, that we'll start to collect this more as a practitioner's viewpoint on how people are approaching this topic across different organizations, what scenarios they're using, what kind of outputs they're getting, because really one of the main points of starting this off was the Climate Change Committee's point about the need for infrastructure organizations to work together more collaboratively on stress testing because of those interdependencies. So it would be great if we did start to build up a bit of a database of those approaches, and hopefully different practitioners started working together there, even if it is on an informal basis.
Brilliant, thank you. And Barbara's also just popped the email in the chat for everyone as well. I guess as there's no more questions and it's now 2 minutes to 2, we'll probably leave it there. But I just wanted to remind everyone that the CIWEM West Midlands branch are hosting the presidential conference on the 8th of April, which will be in person in the Severn Trent Centre in Coventry. And the conference is going to be themed around the ripple effect, which is the key legacy for Hannah and Peter, who are the CIWEM president and junior president. It's going to be an afternoon conference featuring a range of presentations and workshops, exploring how small changes at the community scale can inspire others to take practical action to implement change within their own networks and communities. So we've got lots of interesting speakers lined up. Promises to be, a really good and interesting event. So if you're interested, it's just £30 a ticket and includes lunch. So it'd be great to see some people there and share it with your colleagues. So yeah, I think all that remains to be said. So thank you again, Ian, for sharing that. It's really interesting. And yeah, look forward to seeing everyone again on another webinar.
Lovely. Thanks a lot, Claire. Thanks, everyone.
Thank you. Cheers. Bye.